Hi, now let's implement Naive-based model together. So first, just write the main function. So under the underscore name, under the underscore equal main. So basically, this is a function that run the program. And first, we will create some data. So xtrend is equal to np dot array, and then so 0 1 1 comma 0 comma 0 comma 1 comma 0 0 0 comma 1 1 0. And this one is x trend, and we just create y trend equal yes, no, yes, and then yes, and x test. So x test equal to nb dot array open bracket close bracket 1 comma 1 comma 0, and then we should get some label. So label indices equal get label indices y trend, and you just bring, we will create get label indices later. So just label indices comma, so let's copy this one to here. And now let's create a function called label indices. So they define get label indices. So we take the labels, and now in here I just import numpy as np because it's really important. And now What does it do in here? So it's just group sample based on their label and return indices. So we will write add param label list of labels add return dict class 1 indices and then comma class 2 indices and then just from collections import default dict and then label underscore indices equal default dict and then list and then just for index comma label in enumerate labels label underscore indices label dot append index and then return label indices and then this function will group the sample based on their label and return indices. So let's run to see what happened. Spell is wrong over there. So double equal. Yeah, true. So now as you can see that it take a default dict with a y equal 0 to 3 and no with the 1. So yeah, 0, 1, 2, 3. So in here that we have. So let's share news. So as you see that in here, the default dictionary is y equal 0 to 3 and then the output is no is 1. So in here you can see that this guess correctly because the y is 0, so 0 is correct, 1 is no, y is 2, 0, 1, 0, 1, 2, 3, and it's guess correct. And now we continue to write it. So we need to compute the prior based on the training samples. So just create a prior equal get prior, and then just use label indices in here, and then just bring prior, and then prior, and now we need to get the prior function. So just define on the top def. So just copy this one, get prior, and then put in label indices. So in here, and then I just copy this one because so what does this do over there? This will compute prior based on training sample. So this one param is label indices. So it will, what will it do? It will group sample indices by class, and the second one is, so it will return dictionary with class label as key corresponding prior as the value. So let's actually write the function. So prior equal label len indices for label indices in label indices dot item, and then total count equal sum prior dot values, and then use it for label in prior, and then just prior label divide or equal total count, and then after that you just return prior, and then let's execute that to see what happened. and this is the result that we get. So as you can see that we got z y is 0 2 3, so it's 3 over 4, so it's 75%. N is 0.25 as only have one, so it's very makes sense. So our naive Bayes model is correctly performed correctly. And now we continue to write the next one. So we should get the likelihood. So just smooth thing equal 1 and likelihood equal to get likelihood likelihood, and then we just put x trend over here, and then label indices, and then smoothing, and bring likelihood backslash n comma likelihood, and we can do the likelihood function over here. So just copy this one, and then this one is should be get likelihood, and then it will import features as if import 3 parameters, so we have to define 3 parameters. So features, and then label indices, and the smoothing is equal 0. Should be like this. And now you can compute the likelihood based on training samples and param features. Param features a matrix of features. Param labels indices is group sample indices by class, so it's still the same. Param smoothing, so this one should be integer. Additive smoothing parameter, and then it's return dictionary with class label as a key. Corresponding the conditional probability P, corresponding conditional probability. So P feature class, and we should livelihood with the empty array, and then for label, so I just delete this line because so for label comma indices in label underscore indices dot items. So livelihood label equal features indices comma dot sum axis equal 0 plus smoothing so total count equal length indices, and then we just use livelihood label equal livelihood label divide by total count plus 2 time smoothing, and then this one just return livelihood, and let's run it to see what happens. So I just take a ball to see what happened, and my mistake is I spell wrong to lively. I spell wrong the livelihood over there, so it should be not Y, should be I. And then if I run that, and when you see the result, so the livelihood of the array is up here. So the Y array is 0, 4, 0, 6, 0, 4, and the N array is 0, 3, 3, 3, 3, and 0 point 6, 6, 6, 6, 6, 6, 7. So it makes sense anyway. So that means our naive Bayes model is run, is compute correctly. And now let's continue doing that. The last one I want to do is the both pair real equal get both terrier. So this should get x test comma prior comma livelihood, and then just bring post there and then and then comma posterior. And now we just perform that function. So let's copy this function and just do get posterior, and in here we compute the posterior of testing sample based on prior and likelihood and param x. So it should take x prior and likelihood. So param x is testing sample and then param prior is this should be with label as a key corresponding to prior as well. So this one is prior and dictionary with corresponding prior as the value. Param is likelihood and this one is so dictionary with class label corresponding conditional probability, and the last one is corresponding to posterior as value, and then just initialize posterior equal opener. So in here you have to for x in x and inside the function. First is how can we find the posterior? So posterior is proportional to prior time likelihood, and so we have posterior equal prior dot copy, and then we need to for again. So for label comma likelihood label in livelihood dot items. And you need to for again. So I will fast forward the code because it take quite long time to type this function and it's easy to make mistakes. So let's fast forward it. So I did complete typing on the coding. So in here I just for label livelihood label in the livelihood item. And then you can actually get an index and boolean value in the numerate x. So I just take both area label times the livelihood label index. If the boolean values else minus one minus livelihood label index. So you can normalize and then so that s sum up to 1. And then you have the sum posterior equals sum on the value of posterior and then just for label in posterior. So if the posterior label is float in and then you get posterior label equal to 1. Otherwise you have posterior label divided by the sum of posterior. So the posterior dot append posterior copy and then you return posteriors. And now let's execute the code to see what happened. And in here, as you can see that the Y account for more than 92% and the N is only around 8%. So it makes sense because there are more Y than N. So that's why the posterior in here very high. Also the likelihood is higher there as well. And the prior is also higher. So it makes very sense and our naive Bayes model is working correctly. So now let's come back and then implement the Bernoulli from scikit-learn. So let's import from scikit-learn dot naive Bayes import Bernoulli nb and you will have clf equal just copy this one so it's much easier to type alpha is equal to 1.0 comma fit prior is equal to true and just write clf dot fit x trend and y trend and you can also do bread probe equal clf dot predict underscore probe and then x test. So we will use scikit-learn library to predict the probability of x test and then just bring so SK. So scikit-learn predicted probabilities comma red underscore probe, and then let's execute how the scikit-learn can predict. And let's see. So as you can see that the scikit-learn predict exactly the same with our just have small percentage difference. So as you can see that the posterior for y is 0.9103 and 6007, and our scikit-learn predict the probability the same, and for the n is 0.0789639, and our scikit-learn that predict probability, the probability of our scikit-learn predicted is the same value. So our naive Bayes model is predict correctly, and that is all about in this tutorial for the scikit-learn for the naive Bayes model. If you have any question, just comment below. Please like, subscribe, and share the video so everyone can learn how to build naive Bayes model. And I will see you in the next video. Thank you.